Hi folks. For this lesson you're going to need two things. You'll need your reaction rate notes, which you either picked up the Friday before spring break, or there is a copy on the Moodle site that should be right above this video where you can download them. You'll need the reaction rate notes page, and you are also going to need a writing utensil of some sort. So this lesson is going to be on chemical reaction rates. So follow along in your notes as we're doing this, fill it in, pause as you need to, and answer the questions as they come up. So first thing, the rate of a chemical reaction is simply how quickly that reaction occurs. So just like the rate of how fast you drive is how fast you go, basically how quickly you cover a distance, rate of a chemical reaction is how quickly the reaction occurs. And we could sort of say that chemical reactions then that have a high reaction rate, or you could say a fast reaction rate, are ones that happen really quickly. Those with a low reaction rate are chemical reactions that happen slowly. So examples of reactions with high reaction rates: explosions. If I have a chunk of explosive and I light it on fire, that reaction takes sometimes just fractions of a second to be completely done for that reaction to complete. Gunpowder burning can be another very high reaction rate. A low reaction rate on the low side of things would be, for example, iron rusting. That's a chemical reaction between the iron and the oxygen in the air. But it's a very, very slow reaction, so it has a very low reaction rate. The weathering of rocks, that's a chemical reaction that happens that's one of the slowest chemical reactions out there. And so chemical reactions can vary between reactions that will take sometimes tens of thousands of years to react a few grams of something, to chemical reactions that will react sometimes well over a ton of a substance in just a few seconds. And so high reaction rate means that reaction goes quickly. Low reaction rate means it goes relatively slowly. It doesn't react a whole lot of stuff in a certain amount of time. So oftentimes we as humans, when we're using chemical reactions to do things that are sort of useful to us, we need to adjust those reaction rates to meet our needs. There are times when we want a substance to react more quickly. If we are looking at trying to blow something up, we want that reaction to go quickly. If that explosive takes several minutes to react through, then it just doesn't release enough energy quickly enough to actually do anything useful. But other cases, we want to slow something down. If you take a drug and that drug reacts with your body too quickly, then you get an extremely high dose in a very short time. But what if you need that drug to last for a full day? You want to slow that reaction down so it doesn't take as long. And so we do have to sort of vary reaction rates. We sometimes want a faster reaction rate. We sometimes want a slower reaction rate. Sometimes we just want that reaction rate to be sort of right in the middle, to be right on where we want it to be. So there are four major factors that we can use to change the rate of reaction, and they're conditions. They're conditions under which those reactions happen. And those four things that we're going to look at are going to be temperature, how hot or cold it is, phase, solid, liquid, gas, concentration, which we'll talk about in a little bit, and the presence of a catalyst, which is another term that we'll get to in a second. So temperature is the most straightforward one. If you heat up a reaction, that reaction will go faster. That is, its reaction rate will increase. And if you cool it down, it'll make it go slower. The rule of thumb on chemical reactions is for every 10 degrees Celsius you increase the temperature of a reaction, the reaction rate will double. So 10 degrees Celsius is somewhere in the neighborhood of about 18 degrees Fahrenheit. So if you had a chemical reaction happening at 60 degrees Fahrenheit, and it reacted 2 grams of a substance in a minute, then increasing it from 60 degrees to 78 degrees would double how fast that reaction goes. It would take only half a minute to react to that same amount of substance. And so temperature has a very strong connection with reaction rate. Heating it up makes reaction go faster. Cooling it down makes the reaction go slower. Next one is phase, solid, liquid, and gas. And so the important thing to remember here is that, in a chemical reaction, we have to break old bonds and make new bonds. And the process of breaking bonds and making bonds requires the particles of the reactants have to be in contact. Like the actual physical particles have to run into each other in order for this reaction to happen. They have to collide. And so because of this, gases are going to have the fastest reaction rates. because those particles can fully mix. They're flying around inside the container, they're going every which way, and so any particle in a very short time can run into any other particle in theory, and that's really easy to do. So they have the fastest reaction rates. Liquids, on the other hand, have slower reaction rates. They do mix. Particles can move around and come into contact with other particles, but they don't mix as quickly as gases do. And you sort of know this by experience. You know that if like someone has like an oven and they're baking cookies, they open up that oven and you can smell, even if you're like across the room, those cookies in a very short amount of time, because the gas that comes off those cookies mixes really, really quickly with the air. Liquids mix a lot slower, and so that means their reaction rates tend to be a little bit lower. Solids, on the other hand, they have the slowest reaction rates, since only the particles on the edge of the piece of solid can come into contact. So here we're reacting this green metal, chunk of metal right here, with hydrogen ions. And so the thing is, if they want to react, these hydrogen ions can only hit against the metal atoms that are on the edge. They can't react with any in the middle. They're simply impossible for them to get there because the iron's in one big chunk. And this is one of the reasons why rusting is such a slow reaction, because the iron is one very, very large chunk. It's hard for the oxygen to get into the inside of it. And so that reaction is very, very slow. Now, there is a trick that we can use to get solids to react faster, and that's to take large chunks of a solid and break them up into smaller pieces. So like if we were to take this chunk of metal and grind it into dust, then it would react at a much higher rate, because then the little hydrogen ions can surround all the little tiny pieces of dust, and so almost every atom in the iron could then, or in the metal, could then react with the hydrogen. And so to show you this, let's watch a couple of videos of what happens whenever you take a solid that reacts relatively slowly and you put it into really tiny pieces, into dust, and let's see how that changes the reaction rate. So in this video we're about to watch, what we have here is a furniture plant, and as they basically carve wood to make the furniture they're dealing with, they end up with a lot of sawdust, and they basically are keeping that sawdust, they're storing it inside a hopper up here, and so that you can sort of see at the top. And so that hopper's full of sawdust, so they can drive a truck underneath it and carry away the sawdust when they need to. But the problem is a fire has broken out inside the hopper. So I'll go ahead and get this started up. So the firefighters are going to put it out, but as they spray the water in there, they're going to knock loose the sawdust. When it comes out in lots of little tiny pieces, and we'll watch what happens to the reaction rate. Boom. Very, very quick increase in how quickly that fire was burning, as it went from the sawdust all packed together where the oxygen couldn't get to it, to when it starts coming out of the bottom of the hopper, the reaction rate increases dramatically and we get an explosion. We burned a very large amount of sawdust in a very short amount of time because all little particles were surrounded by oxygen. In this case, we have another hopper. We have some grain, a little grain silo, and so this grain silo is about to fall over. And so all the grain right now is packed together really closely, but as this thing falls over, it will turn into dust. It gets surrounded by oxygen, and the gravitational potential energy of the grain, as it falls, is going to decrease, which then turns into thermal energy. And if we basically increase the thermal energy and increase the reaction rate, boom, all of a sudden that heat ignites all the corn or soybeans that are in this. This is in Indiana, so it's probably one of the two. And so basically we can see that adding just a little bit of heat that happened as it fell was enough to ignite this corn. And corn, I think it looks like corn to me, doesn't really burn all that quickly normally, but whenever we end up with very, very tiny particles of it, then we can get these high reaction rates. And so sometimes we have to worry about what we call grain silo explosions that are caused by this. Is that a silo that's full of grain, when that dust gets kicked up, if a little spark can manage to ignite it and causes a very, very intense fire, because the fact the reaction rate is so high, because it's spread up into little tiny particles that are all surrounded by oxygen. The next factor which affects reaction rate is concentration. So we have 5 different bottles that all have the same volume, but we've and they all have water in them, but we put some food dye, some red dye into each one. In the bottle on the left, there's not a whole lot of food dye in that space, but in the bottle on the right, there's a large amount of food dye in that space. And so we're going to call the amount of a substance that's in a certain space the concentration. And so we would say that this bottle is highly concentrated, has a high concentration of food dye. This bottle has a low concentration of food dye because this bottle has a lot of substance, a lot of food dye in a very small space. This bottle has not much substance in a space, and we can see the concentration increases as we go to the right. So how does concentration affect reaction rate? Well, the higher the concentration of a reactant, the faster the reaction rate. And the lower the concentration, the slower the reaction rate. And if you think about it, this makes sense. In this case, our little sort of greenish particles in here, let's say they want to react with a piece of metal we're going to drop in this dilute solution. Dilute means a low concentration. Then if I put that piece of metal in, there aren't many particles to run into it. They're not going to run into it very often because they're spread apart. But in the concentrated solution, the particles are all close together, which means they're going to run into the piece of metal pretty often. We can use this fact sometimes if we get something like acid on our skin. If we get concentrated acid, it's going to react quickly with your skin. It has a high reaction rate. So if you want to keep that acid from burning you, what you do is you pour water on it. You dilute it. By pouring water on it, you're making the acid particles spread out. It gets to a lower concentration, so they don't run into your skin as often, and you lower the rate of the reaction, and so it doesn't burn as quickly, and so it gives you time to remove the acid from you before it does any damage to you. So increasing concentration increases the reaction rate, decreasing concentration decreases the reaction rate. The final thing that's going to make a difference is adding a catalyst. A catalyst is a substance that speeds up a chemical reaction without being used up in that reaction. So when we put a catalyst into a reaction, it always increases the reaction rate. Catalysts, we can almost think of it a little bit like matchmakers. It's like two people that would get together and start dating. A matchmaker's job is to take those two people who would react and get them to sort of react faster, to get together more quickly. And so a catalyst is sort of like that. It's like a chemical matchmaker that gets two substances together to get them to react. But just like once the matchmaker does their job, they're not really part of the relationship. They're just there to get the people together, and then they're separate and they go on their own way. A catalyst does the same thing. It doesn't get used up in the chemical reaction. It just assists in trying to get the reaction going. The picture on the right here is a catalytic converter in a car. Basically, the platinum is what it is, the metal. It's used to make a reaction to pull pollutants out of your car exhaust. That's usually a relatively slow reaction, and so by adding this platinum catalyst in the catalytic converter, it speeds up the reaction fast enough so that as your car exhaust moves through the catalytic converter, it's able to react those pollutants so they don't go out the tailpipe. Another example are in biology, enzymes are basically catalysts to be able to speed up and slow down certain chemical reactions in the body so that they go the right rate. And so sometimes you want a certain reaction to happen faster, sometimes you want it slower, and so the body can produce enzymes to speed it up or remove enzymes to slow it back down. And so those are our four things that make a difference in chemical reactions, in the rate of chemical reactions.